Okay. Good morning, everyone. Let's get started. So first, sorry for being absent for on this Tuesday. I was got some cold and high fever. So I hope everyone will take care of your health because of this seasonal change. It's very easy to, be infected by some virus or bacteria and all those kind of stuff. Okay, so today we're gonna enter into another, or I guess the last, but very important topics called artificial neural nets, right? So we know that neural networks perhaps is the dominant technique nowadays for machine learning or for broader speaking, artificial intelligence, right? So, but again, because this course is a foundation class, it's a entry-level machine learning class, we're not gonna spend too much time introducing what is the state of art, neural network architectures, how do we run like big models with multiple GPUs. This is not our job. If you would like to know in more detail about cutting edge progress about neural networks, like how do you train a large language model, or how do you train a deep generative models, this is not a topic of our class, but you can seek for more advanced classes like deep learning course, or seek for like deep learning certificate, right? We're gonna mainly focus on the fundamental perspective of neural networks, especially how in general neural network is constructed. How do we train neural networks? Especially what is the essence of the training technique, namely backpropagation, right? Later we'll see the backpropagation essentially is just a smart way of utilizing chain rule, right? The chain rule is the basic idea of backpropagation. Okay, so before we talk about neural networks, let us first summarize what kind of learning algorithm we have discussed so far. Right? We have talked about decision trees, ADA boost, bagging, least mean square, perception, support vector machines, kernel support vector machines, kernel perception, and so on, right? And throughout the discussion, we have also gone through several learning principles, right? We introduced the concept called overfitting, misty bound learning, right? We introduced the basic concept in computational learning theory, like pack learnability, sample complexity. We introduced the concepts called VC dimension, right? And also we introduced the important concepts called training error and generalization error. And based on the relationship between the training error and the generalization error, right? We call it generalization error bound, right? We talk about how do we minimize the bound. This kind of method is called the regularized empirical risk approach, right? And so on. And among those learning algorithms, like least mean square, perceptron, support vector machines, which so far we have spent quite a few classes to discuss about. Those all produce linear classifiers. Of course, linear classifiers are not sufficient to deal with complex scenarios, right? So naturally, we would like to say, okay, can we have some powerful nonlinear classifiers? After all, in real world, you can't assume everything can be dealt with like simple hyperplane, right? So the first idea to produce a nonlinear classifiers is just to extend linear classifiers in some clever way. This trick is called feature mapping, right? If we can just refresh our mind, like what you have discussed previously, right? Even we have some linear classifier, but we can consider first to perform some kind of nonlinear feature mapping, right? So in our original instance space, you know that doing some linear classification is not realistic. But why not we first consider some like a smart feature mapping. And by mapping those instances into a higher dimensional feature space, we expect that in that high dimensional space, we can have some hyperplane to separate out those positive examples and negative examples. Right? That's the basic idea, right? But the feature mapping itself is typically nonlinear, right? That's one strategy, right? And we can summarize this type of techniques as like so-called kernel method. Right? So the kernel method basically means, okay, I want to do feature mapping, right? And after feature mapping, to perform some learning of linear classifiers and prediction, we actually need to compute the dot product between the mapped feature vectors, right? And kernel, we can apply it, we can use kernel trick to avoid explicit computation, because such feature mapping is usually very high dimension, is very costly to directly compute. In some cases, those feature mapping can be infinite dimensional. So it's even unrealistic to compute such a feature mapping directly, right? So I have to leverage the kernel trick, right? So this is like one strategy, right? Based upon existent linear classifiers, let us apply some nice and smart nonlinear feature mapping or nonlinear feature transformation trick to extend our linear classifier to be nonlinear. And one might be curious to know, can we build up a nonlinear classifier from scratch? Right? Why should we first construct a linear classifier and then do some feature mapping? This is like a detour, right? It's like detour. It's not like very straightforward. Right? Why not we just construct a nonlinear classifier from scratch? Right? So neural network is one fundamental strategy of directly constructing a nonlinear classifier. So we're going to first explain what is neural network. Right? And we'll talk about, given a neural network, how do we perform prediction? So this is usually called forward pass. Right? So why do we call it forward pass? It's like you have a set of input features and you flow those input features from the left end to the right end. So this whole procedure, you're going to compute every layer and until you reach output layer. So that's why it's called forward pass. Then we'll talk about how do we train a neural networks. And the training will follow the same framework as we discussed for SVM, as we discussed for least mean square method and so on, right? But the major bottleneck is how do we efficiently compute the gradient of the loss with respect to the neural network parameters, right? And we'll discuss details later. But here we know that maybe you have heard of this term before, right? That's called backpropagation, right? So we'll explain why it's called backpropagation, because the computation is kind of like in the opposite direction, like forward pass. Right? You're gonna starting from the output layer and reversely go through every layer until you go over every weight attached on the neural network. And finally, we'll introduce a few practical suggestions or comments of for using neural networks. Okay. So first, let us talk about the definition of neural networks. We'll mainly introduce the hypothesis space of neural networks and what is the expressiveness of neural networks. Okay. So to introduce the general structure of neural networks, let us first give a graph representation of linear classifier. So you might have seen this figure before, or we mentioned that before, right? But let us just review it. So this graph gives a representation of a linear classifier. How do we see this? So we will the left end as a set of input features. So x1, x2, x3, and x4 represent 4 features. And also, we append a constant feature 1. So later we'll see why there's a constant feature 1, right? And then we connect every input feature, also including a constant feature, to an intermediate node here. So on the edge between every input feature and this intermediate node, we attach a weight. So say between x1 and this intermediate node, there is W1, right? Between x2 and the intermediate node, we have W2 on this edge. So on W3, W4, and between the constant feature 1 and the intermediate node, we attach the bus prime to B. Okay? So, and then on this intermediate node, we put a aggregation operation. So what is aggregation operation? Here, it is just a summation. So here is this node. This just defines. This is just the notation of summation. So this means that, okay, I'm gonna multiply every incoming value with the weight on the edge that connecting this incoming value, and then aggregate all those incoming values through this operation, namely summation. And then the result of the aggregation on this intermediate node essentially is just the W1 x1 plus W2 x2 plus W3 x3 plus W4 x4 plus B. Does it make sense? Right? This is just the graphical representation of this operation. Any question? Yeah. So that's why I would call it aggregation operation, right? So you can see that this intermediate node is receiving multiple values, right? And it's receiving as many values as the number of coming edges, right? So you got 1, 2, 3, 4, 5. You got 5 edges, means that it's gonna receive 5 values. And each value is actually the incoming node multiplying the weight on the edge. So this intermediate node will receive actually W1 x1, right? From here, W2 x2 from here, W3 x3 from here, W4 x4 from this edge, and B times 1 from this edge. And then it's gonna execute this aggregation operation, which is summation, to get the final result. So that means the value attached on this intermediate node will be this guy. Okay. And then we're gonna send this value, the value on this node, to the next node. And this node will just execute another operation, which is called thresholding. So that basically means that, okay, the value of this, the second node, will just taking some threshold over this guy. So you see that the value of this node, or we can say the output of this second intermediate node, is actually the classification results according x1 to x4. So this is a graph representation of linear classifier. Any question? Okay. We're on the same page, right? Okay, so so we can see that this linear threshold units form a very simple network. Okay? So in the very first layer, what happened? So yeah, I don't know what's happened to that projector, but yeah. Yeah, let me finish this before I try this. Okay, so in the very first layer of this network consists of the input features, of course, including some constant feature 1, right? And in the intermediate layer, it has some like node which kind of aggregate the incoming features. And this aggregation is some kind of linear combination, right? And then in the output layer, we do some thresholding operation to generate the classification results, right? So, and the training of this network can be done in various ways. Actually, we have discussed quite a few of them, right? Like we can use perceptron algorithm to do that. We can use SVM, right? And in general, we can come out any regularized risk minimization principle. Like we can come out some like regularization term. We can come out some loss term. We can add them together. We can execute our gradient descent or stochastic gradient descent and so on, right? But for any training strategy, our goal is trying to find the weights on those edges on the network, such that it can fit data well. Also, not like over complicated, or it's not like overfit data. Right? So that's the basic idea. Okay, let me try to shut off the projector and then restart it again. Because that's how I make it work last time. If that one still doesn't work, I would suggest, oh, okay, shows up. Great, yeah, I will report the device issue. Yeah, it's not very stable, okay. Okay, so now let us move our focus on this piece of small network. So now let us view this small network, which is a linear classifier. Let us view it as a basic building unit. It's like building Legos. Lego is always like you can build up a super complicated structure, right? But using a very simple basic structures, right? Like simple bricks or whatever, right? Let us assume this is our basic unit, right? Can we combine them together? Can we attach them together, stack them together, or merge them together to make it a stronger or more complex classifier, right? So this is how we build a neural network. How do you do this? So this is our linear classifier, right? So the input layer tells us where the features come from, right? But what if the input comes from the output from another network? Right? For example, I can construct a second network, right? In the second network, I have X1, X2, X3, X4 as the input layer. And I do some kind of, same network structure. I do some linear combination of those X1, X2, X3, X4, one, and aggregate them into the intermediate node through summation, and then put them into some thresholding node, right? I got some output. I use this output as the first input in the input layer of my second of my network here, right? So I construct a network to get the first input, right? Now, I construct a second network. I reuse this X1 to X4 and 1 as the input layer, but I construct a second network. It's still a very simple network, right? But a different set of weights. And I use that output to serve as the second input in my target network, right? So I got my second input, right? I just keep doing this, right? I construct a third network, again, using X1 through X4 and 1 as my input layer, and to construct the neural network, and then use the output as the third input of my target network, and the fourth network, and combine all those input features together and generate the output as the fourth input of the target network. Okay. So you see, we actually built a composite network, right? And this network consists of like 5 very simple linear threshold units to form a new network. Okay. So this network is a 2-layer feed-forward neural network. And this network is no longer a linear classifier. It's actually is highly nonlinear. Right? So we call, again, we still call X1, X2, X3, X4, and 1 as the input layer of our neural network. But for all the nodes in the middle, we call them as the hidden layer. Right? And the final output, which decides the prediction or the classification results, is called the output layer. So because the hidden layer, although is actually output from the networks coming through the input layer, right? But those hidden layer will serve as the input to the network in the output layer, which decides final output. So we can basically view the hidden layer tries to learn a good representation of the input to the final network that decides our prediction. Right? So we can view like hidden layer as kind of representation. So that's why sometimes people also call neural network as a way of doing like a representation learning. Because eventually you're still using a linear classifier in the top level, right? In the last level, you're still trying to combine, do some linear combination of those some kind of features, and then make a prediction, right? But those features coming from some neural network, perhaps a series of neural network transformations of the original inputs. That's why the hidden layers is also called some kind of representations. Okay, for simplicity, we usually do not explicitly write out these two nodes separately, meaning that we first do some aggregation, like which is typical linear combination, and then do some thresholding. We do not explicitly write them separately. Instead, we usually merge them together. And this merged node is often called a neuron. Okay? So to summarize, what a neuron does is that it's gonna first do some linear combination over the incoming nodes, and then perform some nonlinear activation on those linear combinations. So this is what a neuron does. And of course, we can further extend it to be 3-layer, 4-layer, to whatever layers we want. Okay, so modern neural networks can be as deep as like 100 layers, 200 layers. Okay, so now let us try to formalize this whole procedure, right? What are neural networks? So formally speaking, neural networks are a type of robust approach for approximating real valued, discrete valued, or vector valued functions. They are among the most effective general purpose supervised learning method currently known, especially for complex and hard to interpret data, such as real world sensory data, image data, and so on. And the backpropagation algorithm for neural networks has shown successful in many practical problems, which we're gonna discuss later, right? The invention of neural networks was motivated by biological neurons, because in biological neurons, usually you have some like axons, you have some like dendrites, and so on. But we want to emphasize neural networks or artificial neural networks, more strictly speaking, they are at most, we can at most say they are inspired by biological neurons, but there are many, many fundamental differences. So don't take the similarity seriously. And in many, I think probably we even shouldn't call this type of mathematical models as neural networks, because they are nothing to do with neuroscience. I mean, any serious neuroscientist won't view artificial neural networks as any kind of neural networks, right? And also many numerous papers, even those big shots in this area, trying to mislead the public, and trying to build up false connection between this mathematical model and the true biology or true intelligence. That's actually wrong, and not morality is not good, honestly speaking, because this we can. I mean, to be honest, neural networks are just a type of mathematical models. We can only see this. Right? It's nothing to do with any intelligence or any biological stuff. It has nothing to do with biological neurons, but people call it neural networks. So it is, we got used to call neural networks, but it's really has nothing to do with neuroscience. Okay. So we can add, and most claim that artificial neural networks are a set of a type of family of functions that very loosely mimic a biological neuron, right? And what is a neuron? A neuron in an artificial neural network is actually a function. It accepts a collection of inputs that typically we can represent it as a vector x, right? And it produces an output by doing two things, as we just mentioned, right? First, it applies a dot product with weights W and adding some bias B, right? And then apply some transformation called an activation, right? So the output of this neuron can be written as this composite function. You first do linear combination, W transpose X plus B, and then apply this activation function. Right? And typically, this activation function is a nonlinear function. Any question regarding the definition of neuron? Okay. So going back to our linear threshold units. So obviously, the first operation dot product node, right, is doing the first step, right? The linear combination of all the input features and plus a bias parameter B, right? And then the activation here is just a thresholding function, right? This thresholding is just to check whether this guy is no less than 0. Okay? But of course, there are many, many other choices of activation, right? It's not only thresholding, right? For example, here are a set of commonly used activation functions. The first one is just some like activation, which is only have like a theoretical value, which is called a linear unit. Right? That basically you don't do anything, and you just preserve the original value. The second one is the thresholding, right? Take the sign of the value, right? The third one, fourth one, and fifth one are very, very commonly used. Right? This is called a sigmoid activation. And this is called a rectified linear unit, sometimes called ReLU. Right? This is kind of like a very fundamental and the most basic, most commonly used activation function. Right? If you have got any experience using artificial neural networks, this might be your choice by default. And this is 10H. This guy is used is often used if you want to approximate a function in a very smooth way. If you want your function to be very, very smooth, this one is often the first choice. And many more activation functions exist, like sinusoid, Gaussian polynomial, and like even other continuous relaxation of ReLU functions like CLU, like JLU, and so on. Okay. So now, given this basic definition, like neurons, activation functions, right? How do we view or how do we define a neural network? A neural network can be viewed as a composite function. This function converts the inputs to outputs defined by some directed acyclic graph. In other words, you can visualize this function while some directed acyclic graph. Right? In this graph, nodes are organized in layers corresponds to neurons. Edges carry out output of one neuron to another associated with weights. Okay. So let's see the concrete example, right? So this is one example of the neural network, right? So this is this is a 2-layer neural network, right? We got input layer, we got hidden layer, and we got output layer, right? So we see that those nodes, right, represent neurons, right? And each neuron are connected by the neurons in the previous layer, right? Of course, the value of this neuron is computed following the rule we previously discussed, right? you're gonna first do a linear combination about the connecting neurons and perform some activation function, right? And then these neurons, they will connect to the neurons in the next layer, right? For example, the first output neuron are connected by the 3 neurons in the hidden layer. So they're gonna first do some linear combination and then performing some activation function, right? And similar computation applies to the second neuron in the output. So to define a neural network, we need to specify first, what is the structure of your graph? Second, how do you define the activation function on each neuron? Third, how do you specify the edge weights, right? So once you have determined the structure of the graph, namely how many nodes, how those nodes are connected, right? And what is the activation function associated with each neuron, we see we have a design architecture of the neural network. And then how do we determine the weights on the edges? Those procedure is really called training. In other words, the edge weights of the neural network actually are the parameters of neural network. They are learned from data. Okay, so this is basically the definition of the neural networks. Any questions so far? Okay, great. So here is just a brief history of the neural networks. It starts very early in 1943. These two pioneers, they showed how linear threshold units can compute logic functions. And then in 1949, Hebb suggested a learning rule that has some psychological plausibility. In 1950s, Rosenblatt proposed this perceptron algorithm. So perceptron algorithm was originally proposed to train the so-called linear threshold units. At that time, like people don't call it linear classifier, they call it linear threshold units. Then in 1969, Minsky and Pepper studied the neuron for geometric perspective. And in 1980s, the convolutional neural networks was invented, and backpropagation algorithms was invented, making the training of large networks becomes feasible. And then in 2003 until now, with the revolution of the computational hardware, people found that we can train a super large neural network from the big data using super fast computational hardware, and then the neural network's power has been shown and kind of revolutionize the whole domain, right? Okay, so before we talk about the computation perspective of neural networks, we would like to know a little bit how expressive, how much expressive the neural network can be, right? In other words, what functions do a neural network express? We know that a single neuron with threshold activation, that is linear threshold unit, it's just linear classifier, meaning that it can only classify, it can only represent linear functions, right? However, if we just extend it with 2 layers, just like the very first example we showed, right? We stack linear threshold units into 2 layers, right? and we got like one hidden layer, which coming from the outputs of the linear threshold units from the original inputs, and then we shove those outputs into the next linear threshold units. We got the two-layer linear threshold units networks, right? So it becomes a highly complex nonlinear classifier. In general, it can represent any convex polygons, right? So you see, basically, for any classification boundary like this, like convex polygons, it can represent. If you further add one more layer, right, 3-layer with threshold activations, you can these 3-layer linear threshold units in general can represent any unions of convex polygons, multiple convex polygons. Right? So you can see the power of neural networks, right? You start from a very simple basic structures, right? But if you stack them and you make it deeper, you actually can represent a very complicated functions. There are some well-known theoretical results. Right? In 1989, people have shown that any continuous function can be approximated to arbitrary accuracy using one hidden layer of sigmoid units, just one hidden layer. And further, people find that this approximation error is actually insensitive to the choice of the activation function you use, meaning that you can use sigmoid, you can use sine, you can use tanh, and whatever. Right? And basically, you get kind of a similar level of the approximation error. If we retreat to thresholding activation function, not some computing, just thresholding, just meaning you just do a sine function as activation, right? So if you do 2 layers threshold network, such a network can express any Boolean function. So what does it mean? It means it could be as flexible, as expressive as decision trees, right? Remember, decision trees can represent any Boolean function, right? But of course, your networks are far more expressive than decision trees because you can put it 3 layers, 4 layers, arbitrary layers, actually. So here are some results about the VC dimension about the neural networks. So the VC dimension of the threshold network with edge E is proportional to the size of the number of the edges times the logarithm of number of edges. So that basically means the more edges of the you have in your threshold neural network, the more expressive your network is. But if you use sigmoid as your activation function, and then you need to also consider the number of nodes. And it has some upper bound and lower bound for the VC dimension, but it doesn't have a exact characterism of the VC dimension. So it's upper bounded by the square of the number of nodes times the square number of edges, and lower bounded by the square of number of edges. So you can see that the larger size of neural network, the more expressive, the more flexible of the neural networks. So this is actually quite match people's experience, right? And usually, if you have a small amount of data, people won't suggest you to build a super large neural network with tens of millions of model parameters. Why? Because it's usually overfit data, right? But if you have a huge amount of data, right? And if you want a model to sufficient train, right? You want to capture the whole data information, you would like to build up a giant neural network. Okay, so this is the basic definition of the neural networks, right? So there's one little exercise for everyone to do is that please show that if we only have linear units, meaning that we have neurons which have a linear activation function, then no matter how many layers you put, you stack those neurons, it doesn't change the expressiveness of the network. It's gonna still be equivalent to a linear classifier. Okay, any question regarding the definition of the neural network? Everyone's good? Okay, perfect. Next, let us talk about given neural network first, how can we do a prediction, right? After all, we need to first do the prediction and then we will say how well it can predict, right? And based on prediction error, we can adjust our model parameters and conduct training, right? So the prediction procedure is called forward pass. Later we'll explain why it is called forward pass. Okay, talking about predicting with a neural network. So let us use a concrete example to illustrate this procedure, right? So we're talking about this three-layer neural network. We have one input layer, we have a hidden layer, and we have an output layer. In the output layer, we only have one neuron, or one node Y. Okay, so to be convenient, right? We're gonna introduce some naming conventions because this is important because a neural network has many nodes, has many neurons. Right? Let us define let us denote the neurons in the input layer as X, and the neurons in the hidden layers as Z, and the output neuron, meaning that the neurons of nodes in the output layer as Y. Okay? Of course, we're going to index those X, Y, Z represent different neurons in that layer, right? And those shaded ones, like X0 and Z0, are just constant features, is they are fixed to be 1. Right? Those are just to emphasize that, okay, we're doing some linear combination plus some bias parameter. Right? It's the same as a linear classifier. Right? And we're assuming that we're going to apply some sigma activation functions over those intermediate neurons. And one thing which is quite special is that in the output layer, the computation of each neuron will simply apply the linear activation. So what is linear activation? Any hint? Yeah, exactly, right? We just mentioned, right? Linear activation means that you actually do not perform any activation, right? Just did, right? So why do we enforce a linear activation in the output neurons? No reason, just tradition. There's no special reason for this because the neural network people, this community, when it was built up, they just use this tradition. That's it, right? And we'll see the modern neural networks, and it's always like this. They have like coming out like thousands of all kind of weird architectures, but you will see at output layer, they still do linear activation. In other words, each output neuron is just a simple linear combination of the neurons in the second last layer. And that's it. But of course, in your own practice, you can choose to use other activation. It's up to you. But here we just stick to the tradition. Okay. So here is our naming convention. Okay. It's mainly for denoting the weights on the edges. So we denote the weight of each weight in this network by W, but we use subscript and superscripts to represent the source and destination. So first, in the superscript, we use superscript to index the target layer, namely at which layer, to which layer the edge will point to. Like for example, here. Okay. This weight is on the edge, which points to the output layer. So the target, so the superscript indicates the target layer, so it's O. It just indicates the output layer. Right? And this guy, this weight is on an edge which points to a hidden layer, right? So the superscript which indexes the target layer, so now is H, right? So the subscript actually represents the source and destination from two. So if we're going back to this weight, right? So you can see the edge starts from node 0 in hidden layer and to node 1 in output layer. So that's why we say the subscript are 0, 1. And here, if you look at here, right? If you look at here, this weight is on the edge, which starts from node 2 in the input layer and goes to node 2 in the hidden layer. So from node is 2 and target node is 2. So it's W22, right? So that's our naming convention. Okay. So basically, a subscript consists of the source node index and then the destination node index. And the superscript is just the index of the destination node layer. Okay, so now, given all those definition of the notations, right? Let us look at how do we compute the output, right? So suppose we're given the input X. So input X here is vectors, just means like we have a X0, X1, X2 given, namely all the input features, right? How is the output is computed, right? So we just sequentially compute every neuron in one layer above. And once we compute the neuron for all the neurons for this one layer above, we use those neurons to compute the every neuron in the next layer above, and go on until we compute the output neuron, and that's it. So we have given x0, x1, x2, right? That's the beginning. So we're gonna compute every neuron in the one layer above, right? Which is the hidden layer here, right? That means we need to compute Z1 and Z2, right? Remember, Z0 is just constant neuron, which is one, right? So Z1, according to the definition, is computed by a linear combination of the connected neurons to Z1, right? And then apply activation function sigma. Right? So you got Z1, right? So remember x0, x1, x2 all connect to Z1, right? And we have a weight on those edges denoted. Remember, now we should memorize our notation convention, right? So this is a W, H, 1, 1, this W, 2, 1, H, right? Source node, destination node, and target layer index, right? So you got W01H times X0, remember it's constant 1, right? And this guy is W11H times X1. And this guy is X2 times W21H. This is the linear combination, right? And then apply the nonlinear activation function sigma here, right? Here we choose sigma activation, right? So we got Z1. And similarly, we compute Z2, right? And of course, we're gonna going through a different set of weights because the edge is changing, right? So this edge is here, right? Here, here, and here, right? Applying our, consider our notation of the weights, right? So this is a W02H, right? This is W12H, this is W22H. So you got this one, right? And then you apply the CMOL activation function. You got sorry, it's here, right? This got Z2, right? So once you have computed Z1 and Z2, because Z0 has already known to be constant 1, right? You have finished the computation of the hidden layer, right? The whole hidden layer, right? Now, based on these results, we're gonna compute all the neurons in the next layer, right? Which is just the alpha layer, right? So the alpha layer, Y, is just a linear combination of all the neurons in the hidden layer. Right? Remember, we'll apply the linear activation. Right? Basically means you don't do any transformation. Right? So once you have finished computation, we only have one node or one neuron in the alpha layer, right? So only compute one neuron, you're done. And then our prediction is done. So this procedure, we can see the process, right? You start from the bottom layer, which is input layer, and then use the current layer to compute every neuron in the one layer above, right? And once all the neurons in the one layer above is computed, then you proceed to the next layer and then compute all the neurons in one layer above. You just continue doing this until you finish computation of all the neurons in the alpha layer. So that's why this is called a forward pass, because we know that the procedure from the bottom layer to the top alpha layer as the forward procedure. This is called forward pass. Okay, any question regarding the forward pass? Okay, everyone is comfortable? Okay, perfect. Okay. Then we can talk about how to train neural networks. Okay. And of course, the the core technique of neural network training is backpropagation, but we should first talk about what is general training framework. Okay. So the training of neural network, we should first give some kind of formulation. Right? Suppose we have some neural architecture design, right? Namely, we know what is the layout of neurons, how are they connected together, and what are the activations on every neuron, right? We have also collected a data set of labeled examples, namely pairs of input feature vectors, xi, and output yi, right? The goal of our learning is to learn the weights of the neural network. And here we should be clear, should be aware of one thing. If you have a neural network architecture to be fixed, and also you have selected the activation functions for each neuron, then the neural network's output essentially is a function parameterized by its weights, right? Because the neural network essentially is just a composite function, right? And you just composite each neuron. Each neuron is just a basic function, right? The function combines the values of the connected neurons through some linear combination and nonlinear activation, right? And then those neurons are all combined together to calculate the neurons in the next layer. They just keep doing this until you get to the output neuron. So neural network essentially is just a composite function, right? Once you have already determined the structure of the neural network, namely how this composition is done, right? And also the activation functions, they actually have fixed the form of the function, right? And this function is only parameterized by its weights. And our goal of the training essentially is to identify the weights according to the data. Any question about this point? Okay. So how can we do that, right? This is very similar to what I have done for SVM learning or linear regression or boosting and so on, right? We have a neural network classifier that is completely defined by its weights, right? So we want to learn its weights by minimizing some kind of loss, right? So suppose you got a training data set, right? And for every training data example I, right? And we have some prediction made by neural network. And we have some ground truth label yi, right? We count on some loss function. Then we sum up all this loss over every training example. Then we try to minimize the entire loss. With respect to the neural network parameters W, right? We want to find out the optimal network parameters W, which can minimize the loss. Does it make sense? Right? Okay, so suppose you have a set of training examples, right? For every training example, we use neural network to make prediction, right? And also, we know the ground truth. We calculate the loss. You just sum up all the loss. And you just minimize the total loss on the entire training set. Right? And to find out the optimal model parameter step, that's it. Right? That's the same as we train for perception support vector machines, least mean square regression. This is the same thing, right? The only difference is that this neural network functions is highly complicated. Right? It's not a simple linear combination of the weights and features. Right? Instead, is a very complicated composition of those basic neurons. Right? Remember, each neuron is a simple function, is a nonlinear activation over a linear combination. Right? But you have a hierarchical combination of those neurons. Right? It's highly complicated. Right? And sometimes you perhaps also add some regularizer over the weights. Okay. So, so far we saw this strategy worked for support vector machines, perceptrons, the least mean square regression. So all those are linear models, but when we train neural networks, we actually apply the same idea. Okay, so let us go back to our running example. Right? Given an input X, we do some kind of forward pass to compute the output, right? We know that we're going to start from the input layer, right? And compute every neuron in one layer above. Right? Once every neuron in one layer above is down, we use those neurons to compute the neurons in the next layer and continue, right? So after doing this, we got our output. And suppose the true label for this example is number y star, right? And we have some square loss for this example, so here. And then the question is that when we minimize this loss, right, we're gonna calculate the gradient of this loss with respect to every weights appearing on those edges, right? So that's the whole procedure. Gonna write it as W, this target layer number J, and this source and destination. Right? So that's the whole procedure. But other than that, it's the same, right? All the other steps are the same. The K is that how do we efficiently compute this guy? How do we efficiently compute the partial derivative of the loss with respect to every edge weight in the neural network? Okay. So before we go to the details, like let us consider, okay, we're gonna apply the stochastic gradient descent framework for this. So suppose we're given a training set S, right? Xi, yi, pairs of Xi, yi. We initialize our parameters W. And in neural network, it basically, it typically initializes some like random values, not full zeros. And we go through the data set for many, many epochs. And inside each epoch, we shuffle the training set randomly. And for each training example, Xi, yi, we treat this example as the entire set, then compute the gradient of the loss over this example. And with respect to every weight in this neural network, then we update those weights according to some step size. And of course, the step size need to be carefully scheduled. We have mentioned that before, right? It must satisfy some criteria. And there could be many tricks. And then we finish one update. And we just keep doing this until we go through the entire training set for once. We will finish one epoch. And then we go to the second epoch. Keep doing this, and suppose we have finished all big T epochs. We consider our training has been done. We return this current set of weights as our neural network parameters. That's the training process. Mm-hmm. Yeah, you can do that. You can definitely do that. So this is just a very basic framework. And in practical training, you can add a lot of conditions to early stop, actually. For example, you can use the third validation set, right? And you can train like every 10 epochs and test your performance on this validation set. If it is no longer improved, I'm gonna stop and quit. It's actually many, many such kind of tricks. Any other questions? You mean this gamma t? Yeah, it's a learning rate. Yeah, it should be very small, and it should satisfy some conditions. We mentioned that before, right? Your gamma t should be their summation. Well, the direct summation should be unbounded, and the square of the summation should be bounded. Right? We mentioned that why we're doing this. I'm gonna not repeat this again. But usually, modern neural network libraries, you don't need to worry about this. There are like a variety of choices you can do that. They all satisfy those conditions. And the tweaks for this is very, very important. But there have already been a lot of like techniques of doing this. But right now, the most popular techniques for doing this is called ADAM, ADAM. Okay. This is the most popular techniques of doing this stochastic training. Basically, the key idea of gamma t, this is the whole ADAM is just a trick of doing this gamma t smartly. But there's some like theoretical problems with ADAM, but empirically it was it's kind of like all people like recognize is the most robust and the top performing ones. Okay, any other questions? Great. Another thing we want to point out is that because the neural network is highly complicated, it's highly nonlinear. So your loss function is not convex anymore. So if you look at landscape of loss functions, it could be something like this. It's very complicated. So basically means like you could get into any local minimum. Right? So it could be here, it could be here, or it could be here, right? So that means initialization can be important. Right? Different initialization can lead you to different local minimum, which give you different performance. That's why like the trick of initialization is also important for neural network practice. And if you look at some like popular libraries like PyTorch, they provide you like I think at least like 10 different choices of initialization strategies. And they're also they have their default strategy. Okay. So far we have introduced the whole training framework for neural networks, right? So it looks like there's nothing different from what we have discussed previously, but we have not solved everything. Right? We haven't mentioned the most critical part. How do we compute the gradient? Right? Actually, this is the most. This is actually the bottleneck. So why neural network works? Why neural network works? If you just use one neuron, or just a few neurons, if you just use one hidden layer, neural networks perhaps is not as powerful as support vector machines or any other nonlinear classifiers. It won't like attract so much attention, and why is applied so broadly. Right? The power of neural networks shows up is actually when we build up really giant networks, meaning that you have a super wide and super deep networks. Super wide and super deep networks means that you have to train a large number of the parameters. Right? For example, you got 250 layers, right? And each layer contains 100 neurons, 200 neurons. It's very common. I'm pretty much sure about that. And imagine how many parameters you have. Right? And if you directly compute this, if you just naively compute this gradient, right? Even for compute the gradient for a single example, it will be deadly slow, and it won't be practically feasible for you to train a giant neural network not to mention for like for big data, right? Even train such a neural network on 10 examples, you will wait for like you'll wait for several hours. That's not acceptable. So one critical bottleneck of neural networks training is that how do you efficiently compute the gradient of the loss with respect to every weight? That's the key. Not how to handle large data, right? Not to handle large data, not to handle other things, right? Right. So to address this problem, right, we need an efficient algorithm. So this algorithm is called backpropagation. Right? So what is backpropagation? Backpropagation essentially is a way of doing chain rule. So before we talk about that, right, so let us just review what we have seen. Right? If we have a neural network, we can make a prediction for an input. If we had a true label for the input, then we can define the loss for that example. And then we want to take the derivative of the loss with respect to each weight. Then we can take a gradient step in the stochastic gradient step. Right? That's the whole procedure. And right now, we want to make the computation of the gradient step to be as efficient as possible so that the stochastic gradient descent can be efficient. Right? That's the context of conducting backpropagation. So any questions so far? Okay. Okay, we will just use 1 minute to quickly review the chain rule. Right? So what is chain rule? Chain rule is the rule to compute the partial derivatives or derivatives for a composite function. So if z is a function of y and y is a function of x, then z is a function of x as well. So in that case, how do we compute partial z or partial x? I believe everyone has learned this before, right? So partial z or partial x equals to partial z or partial y times partial y or partial x. And we can visualize this in a simple graph. Right? We can represent the dependency between those variables using a graph. We got z, y, and x. Each node represents a variable. Right? If z is function y, right, we can connect y and z. We can draw an edge from y to z. And y is a function x. We can draw a edge from x to y. Right? And each edge will attach a partial derivative. Then if we want to compute partial z or partial x, we want to find out the path from x to z, which is here, right? Then we'll multiply all the partial derivatives along that path. Then we get we got a partial derivative of partial z or partial x. Okay. So let's stop here today, right? So in the next lecture, we'll give a more thorough review of the chain rule and then give details about backpropagation.